Friends, let us continue with the fifth lecture in module 1, where we will discuss more features about beam element as a second part of the lecture. In the earlier lecture, we said that M I is K I of delta I, M being a vector, K being a matrix and delta being a vector is a valid equation. If you look at the typical stiffness matrix of the ith element, which we derived in the last lecture, we said let us have P Q R S, let us also indicate P Q R S, and stiffness coefficients are K P P, K P Q, K P R, K P S, row first and column next, say Q Q P, K Q Q, K Q R, K Q S, K R P, K R Q, K R R, K R S and K S P, K S Q, K S R, K S S. So, there are rather 16 coefficients as you see in this equation, out of which one good thing is we need to only evaluate set of rotational coefficients. Others can be expressed in terms of these rotational coefficients. So, what are these rotational coefficients? The rotational coefficients which we are interested is K P P of the ith element, K P Q of the ith element, K Q P of the ith element and K Q Q of the ith element. These are the 4 coefficients. These are the 4 coefficients which are important. The remaining can be expressed in terms of these. For example, if you want to evaluate the end shear, we can say K R P is actually K P P plus K Q P of the ith member divided by length of the member, and K S P of the ith member is minus of K P P plus K R P by L I. Carefully look at these figures. K P Q, K Q Q, K P P and K Q P. These are the 4 coefficients K P P, K P Q, Q P and Q Q. These are the 4 coefficients which we are interested. In fact, we are interested in these 4. If I am able to evaluate these 4, remaining 12 can be expressed in terms of this. Okay. So, now the negative sign in this case is due to the fact that direction of K S P is opposite to the end shear developed by the restraining moments. Let us try to understand how this happens. Let us look at this figure. Let us this figure. Look at this figure, and I try to enlarge this figure again. I have an element with both ends fixed. We have given unit rotation at the end P. So, now to control this will induce a moment which will be equal to K P P. This will also cause another moment which is K Q P of the ith element. So, now this will have an anti-clockwise moment which actually will be equal to K P P plus K Q P, is it not? This has got to be counteracted by the shear, which will be creating a clockwise couple, which will be actually equal to K P P plus K Q P by L I, where L I is the length of the member. So, this will be also K P P plus K Q P by L I. If you look at the original degrees of freedom, we already said upward end shear is positive. So, this will be negative. That is what we are writing here, K R P, which is this value, and this will be K S P. Please recollect, the second subscript indicates we have given unit displacement in the pth degree, and the first subscript indicates the respective forces in the degrees of freedom. So, this will be K R P, this will be K S P, which actually equal to negative. So, this is what we got. So, the end shears can be expressed once I know the rotational coefficients, these 4. So, by this manner the remaining coefficients can also be expressed in terms of these rotational coefficients if you know them. So, out of 16 coefficients we have, we need to only evaluate these 4 coefficients, okay. Only these 4 are important, remaining can be derived if we know these 4 coefficients. So, now the task is to evaluate these rotational coefficients. So, we can extend the similar logic further, like similarly refer to the figure. I should say the number, I should say figure 2, this figure, referring to figure 2, which causes unit rotation at kth end. You can see here unit rotation at kth end, okay. K R Q and K S Q can be expressed as sum of the rotations, which is K P Q and K Q Q, okay. So, K P Q plus K Q Q of the ith member by L I, and this will be same K P Q plus K Q Q of the ith member by L I, but with a negative sign. Now, similarly refer to figure 3, where unit translation is given at jth end. You can see the figure 3, unit translation at the jth end. The rotational coefficients are K P R and K Q R, okay. So, now I can easily find this K P R as the rotation caused by this change in slope. Okay. So, Kpr can be expressed as Kpp of the ith member with this rotation plus Kpq of the ith member with this rotation, which will be Kpp plus Kpq divided by Li. Similarly, Kqr will be also equal to Kqp of 1 by Li plus Kqq of 1 by Li of the ith member, which will be written as Kqp plus Kqq of the ith member by Li. Now, I can say Krr is Kpr plus Kqr by Li, which is nothing but, because Kpr is given by this expression, which is Kpp plus Kpq by Li. So, which should be Kpp plus Kpq by Li square, there is already Li here, plus similarly Kqr is Kqp plus Kqq. So, Kqp plus Kqq by Li square, which means Kpp plus Kpq plus Kqp plus Kqq by Li square. Similarly, Ksr will be negative of Kpr plus Kqr, which will amount to minus of Kpp plus Kpq plus Kqp plus Kqq of Li square. Now, referring to figure 4, where unit displacement is given at kth end, you can see this figure, unit displacement at kth end, and you have a slope which is negative. Okay, this is this way. The moment is this way clockwise, whereas the slope is on the other side. So, Kps, that is this coefficient and this rotational coefficient, Kps is minus of Kpp plus Kpq by Li. Kqs is again minus of Kqp plus Kqq of Li. Therefore, Krs will be Kps plus Kqs by Li, which will tell me minus of Kpp, Kpq, Kqp plus Qq by Li the whole square, whereas Kss will be positive of Kpp plus Pq, Qp and Qq of Li square. So, friends, if you look at these equations, which are end shear, they are expressed in terms of the rotational coefficients, The end shear is again expressed in terms of rotational coefficients. So, the interest is the end shears can be expressed in terms of rotational coefficients. So, we are now interested only to evaluate the 4 rotational coefficients to get the full stiffness matrix of 4 by 4 containing 16 coefficients. So, it is very simple. We do not have to derive all the 16, we derive only the 4, we can get the remaining 12 automatically from these set of equations what we derived just now. So, I can now make a matrix saying that the K matrix, which will be P, Q, R and S, P, Q, R and S. This is K P P, this is K P Q and this is K Q P, this is K Q Q, row first and column next. I evaluate only this 4, okay. Remaining are derivable very simply. This is K P P plus K P Q by L, that is sum of these two, okay. And this is K Q P plus K Q Q by L, that is sum of these two by L. This value will be K P P plus K Q P by L, which will be sum of these two, and this value will be minus of K P P plus K Q P by L, which will be as same as this with a negative sign. Similarly, this value will be K P Q plus K Q Q by L, which is sum of these two, and this will be minus of K P Q plus K Q Q by L. Okay. Now, let us come to this argument. This will be K P P plus P Q plus Q P plus Q Q by L square, which will be sum of these two by L, and this term will be negative of K P P plus K P Q plus K Q P plus K Q Q, the same with a negative sign. The fourth will be the same value with a negative sign, that is minus of K P P plus K Q P by L, minus of K Q P plus K Q Q by L. Then this value will be the sum of these two by L. Therefore, minus K P P plus K Q P plus K Q P, this is K P Q, this is K P Q, K P Q Q P plus K Q Q by L square. This will be plus of this value, which is P P, P Q, Q P, Q Q by L square. So, friends, if I am able to evaluate these 4 values 1, 2, 3 and 4, that is this value and this all the 4 remaining all can be calculated with the help of this particular table. Okay. So, the job is now to evaluate these 4 rotation coefficients KPP, KPQ, KQQ and KQQ. So, we need to evaluate this, that is all. Okay.